Scientists talk a lot about the Big Bang like it's an obvious fact, and most people have a basic understanding of what the Big Bang was, the universe suddenly popping into existence, expanding from a single point. Give it 13.8 billion years and all of a sudden we're here, smart enough to think about it. But how do they know the Big Bang actually happened, you ask? A truly great question. And to answer it, I'll first have to explain a few basic concepts, the first of which being the Doppler effect. So if you've never heard of the Doppler effect, no worries, because you most definitely heard it. So that was the Doppler effect. The pitch of the sound changes based on speed. You see, if the car were to honk while being stationary, the sound would be at a constant pitch. Would you look at that? Pitch ain't changing. Now if you're deaf, the difference between the moving honk and the stationary one might have been a bit hard to spot. But don't despair, because we got a chart. So this chart shows the frequency or the pitch of the stationary honk. And what I want you to take from it is that it doesn't change. It's constant. Now here we got some movement, and as you can see it looks a bit more interesting, right? Because in the beginning we have slightly higher frequency, and in the end we have slightly lower frequency, and of course we have this little transitional period in between here. And to explain what is going on here, I would like to show you a few animations. So what we see here is an object emitting some waves. They could be sound waves. But the important thing about this animation is that the distance between two wave crests, the wavelength, is unanimous all around. It's the same. In this case, it happens to be 50. But what would happen if we were to give it some speed? I am glad you asked. And here it is doing the exact same thing, just with a velocity. And what you notice is that the waves in front get compressed, and the ones behind it get expanded. The reason we see this is that waves travel at a constant velocity. You see, the frequency or the pitch of the wave is simply the number of waves that pass by every second. So if the wavelength is large, the frequency will be small because it takes longer for each wave to pass by, and vice versa. So in the first example, it doesn't matter where you stand because you will observe the same frequency regardless. But in the moving example, the frequency behind the object is lower because the wavelength is longer. And in front, the frequency is high because the wavelength is low. So standing in front of the object, you would hear a high frequency, high-pitched sound, and behind it, you would hear a low frequency, low-pitched sound. And this is of course exactly what we saw with the car. When it's coming towards us, we hear a high-pitched sound, and when it's moving away from us, we hear a low-pitched sound. The second thing I would like to explain is that, at least for our purposes, light is a wave. And one of the reasons is that if you throw particles through two holes, you would expect the particles to go through one of the holes and land directly behind it. However, with light, you don't see this. Instead, you get what's called a diffraction pattern. And what happens is that the light wave goes through both holes and interacts with itself. This creates bright spots where I drew the lines and dark spots in between. So if light is a wave, that means that the Doppler effect also has an effect on light. What we see here is the frequency spectrum of light, and the frequency increases towards the right. So if the source emits green light and moves towards us, the frequency will increase and the light will appear blue. And if it's moving away from us, the frequency decreases and the light appears red. Now here we are in deep space, and all the little bright dots you see are galaxies. And something very interesting happens when we look at the very, very distant ones. You see them shifting towards the red end of the spectrum, don't you? And it doesn't matter where you look, it's the same all over. Why is that? Well, it means that they're moving away from us. But more importantly, the relationship between distance and velocity is linear. That's to say that if you have some galaxy and it's moving away at some velocity and it's some distance away, then if you have a galaxy that's twice the distance away, it's going to be moving away with twice the velocity. And this implies that the universe is expanding. Look at this diagram. You see the red part is an expanded version of the white part. And if you consider one of the dots, you see that everything is moving away from it, just like we observe in real life with galaxies. So if the universe is expanding, that means that in the past it was slightly smaller than now, and if you go back far enough, the universe would have to have been just a single point. And that's the Big Bang!